Let's talk about some key distinctions between ordinary chemical reactions and nuclear reactions. Ordinary chemical reactions are reactions of the type we've been discussing all semester. And the first difference is that the identity of the reactants is retained in ordinary chemical reactions, but in nuclear reactions, one element is converted to another. Specifically, if we have a ordinary chemical reaction, the same number and type of atoms in the reactants is exactly the same as that of the products. In nuclear reactions, we're going to see that elements are converted one to the other. Another key difference is that relatively small amounts of energy are involved in ordinary chemical reactions, but huge amounts of energies are involved in nuclear reactions. The key difference is that there is some missing mass in nuclear reactions, and this mass is converted directly to energy. Okay, mass converted directly to energy is done consistent with Einstein's law, which energy is equal to mass times c squared. M here refers to our mass defect. We will see that in nuclear reactions there's some amount of mass that goes missing over the course of that reaction. And that missing mass, or that mass defect, is converted to energy. And if we look at this other value, c is the speed of light in a vacuum, and as we see, it's a very large value. So we're multiplying our missing mass times a very large value that's squared. That's going to result in a huge amount of energy. As we've just discussed, nuclear reactions are reactions in which mass is converted directly into energy. Let's review quickly isotopes. Isotopes are atoms that have the same number of protons, therefore they're going to be the same element because an element is defined by the number of protons in its nucleus. However, isotopes have different numbers of neutrons. We can represent specific nuclides by the following notation. Okay, we see the elemental symbol of the element, and there's a preceding superscript and subscript. The preceding superscript, A, is the mass number, which is the number of protons plus the number of neutrons in the nucleus. Z corresponds to the atomic number, which specifies the element because it gives you the number of protons that are in the nucleus. An example is carbon-14. Our mass number is 14, atomic number of 6. So we see 6 protons in the nucleus, same as every atom of carbon. However, in this nuclide, we have 14 minus 6, or 8 neutrons in the nucleus. We can always remember which is the superscript and the subscript, because this kind of sets up a little subtraction for us in terms of giving us the number of neutrons that are in a specific nucleus. Now, we've said that nuclear decay is when we have a radioisotope, which just is some isotope that is radioactive. It's going to undergo decay. A radioisotope is going to decay, and we're going to generate a new element, likely have emitted particle or emitted particles, and a lot of energy. Let's talk about the different types of emitted particles that accompany every nuclear decay process. All right, so we have 3 different types of particles we're most concerned with. The first is alpha particles. Alpha particles are essentially stripped helium nuclei, helium atoms that have their 2 electrons taken away. So 2 electrons lost means it has a net plus 2 charge. High-speed electrons are beta particles. They have a minus 1 charge. And gamma particles are typically not shown. They can easily be viewed as high energy packets, simply energy packets that have no associated mass or charge. And these are the symbols that are associated with the alpha, beta, and gamma particles. It may be useful to refer to this notation. So A is the mass number, neutrons plus protons. Z corresponds to the atomic charge. So a helium atom has 2 protons, 2 electrons, or a mass number of 4. 2 protons means that our atomic number is 4. Sometimes you'll see this represented as associated with helium. Sometimes you'll see it associated with the alpha symbol here, lowercase Greek alpha. Beta particles, high energy electrons, they don't have any protons or neutrons. The atomic number is essentially -1. When we balance nuclear reactions, we need to make sure the sum of the nuclear charges on the right-hand side and left-hand side match. These numbers correspond to the preceding subscripts, Z, and we have to do a similar thing with the mass numbers. The left-hand side must match the right-hand side, and here we're looking at these preceding superscripts, or what corresponds to the mass number. Let's apply these conditions to this example. The sum of the nuclear charge, the preceding subscripts, has to equal the same thing left and right. That means 82 has to equal the sum of -1 plus whatever preceding subscript is going to be associated with our missing nuclide. So therefore, we know that number has to be 83. The sum of the mass numbers has to be the same, which means 211 has to equal the sum of 0 from here plus the mass number associated with this nuclide. So the mass number of that nuclide must be 211. So we can write our missing nuclide. We know it's going to have a mass number of 211, and it's going to have a nuclear charge of 83. We look up in our periodic table to see which element has a nuclear charge of 83, and we see that's going to be the element bismuth. So we can write in the elemental symbol of bismuth as it has a nuclear charge, Z is equal to 83. When we determine the nuclear charge on our missing nuclide, we know what the element is. So now we have a balanced nuclear reaction. For this next nuclear reaction, we first want to remind ourselves of what the missing atomic number is, the missing preceding subscript associated with radon and helium. We go to the periodic table and we see radon has an atomic number of 86, so we can fill that in here. Helium has the atomic number of 2. So again, we get the missing values of Z here from our periodic table. Now we can apply the rules where the sum of the mass numbers and the sum of the atomic numbers has to match reactants to product. So the sum of our mass numbers, these preceding superscripts, has to be the same reactants to products. So we have 220 is equal to 4 plus some unknown value. 220 is equal to 4 plus some unknown value, so that must be 216. Now for the preceding subscripts, the atomic numbers, 86 has to equal 2 plus some unknown value. That unknown value has obviously got to be 84. Finally, we go to our periodic table to see which element has an atomic number of 84. And we see that that element is polonium. So we know that our nuclide product is going to be polonium 216. Here we have a slightly different type of nuclear reaction. Particle capture, i.e. the particle that is involved in the nuclear reaction is part of the reactants. Same method as before. First, we're going to determine our Z values, these preceding subscripts, from the periodic table. So now we apply our rule where the sum of the mass numbers and the atomic number has to balance reactants to products. So in the superscripts, we have 14 plus some unknown value is going to equal 1 plus 14. So our unknown value here is 1. For our atomic number, 7 plus some number has to equal 1 plus 6. Obviously, our value here is 0. Our unknown particle, therefore, has a mass number of 1 and an atomic number of 0. This is going to correspond to a neutron. The sum of the protons plus the neutrons equals 1. Without there being any protons, we know that it simply has to be a neutron. And we apply a rule where the sum of the mass numbers has to be the same, reactants to products. That means 40 has to equal 0 plus some unknown number. We know our unknown number here is going to be 40. 19, it has to equal minus 1 plus some unknown number. That unknown number is 20. So these two values have told us what the mass number and the atomic number of our unknown particle is. Now finally, we determine our unknown element from the atomic number, the preceding subscript. We know our preceding subscript is 20. We go to the periodic table and we see the element associated with an atomic number of 20 is calcium.